All right, so if you want to open to page 7 in your notes, and if you would take notes on this, the questions 1 through 6 ask you to determine whether the following functions are growth functions or decay functions. Well, this is pretty easy. I'm going to look at number 3. All you need to do is you need to look at this number right here. And if that number is greater than 1, then it's a growth. So for number 3, it is a growth because 1.3 is greater than 1. If you look at number 6, for example, let's take a look at that. Now, they don't actually give you that value, but you can do 1 minus 0.4, and we know that that's 0.6. So that value is less than 1. So if the value is less than 1, then a function would be decaying. Okay, growth is getting larger, decaying is getting smaller. All right, now looking at number 7, take a second. If you have to pause me and read the question. And what it's giving you is like a time 0. So basically it's telling you at January 1980, that's going to be your time 0. There's a population of a city, and it grows according to that model that they give you in that second line right here. Okay? All right, now they want you to explain what 720,500 is. Well, 720,500 would always be your initial, and since right now, it's always going to be an initial amount. So the number to the right of the equal sign, whenever we're doing growth and decay, will always be an initial amount. And in this case, they're talking about a population, so we're going to say it's initial population of Brownville. Okay, I'm going to abbreviate Brownville. Now, let's be very specific, and we'll say in January of 1980. Okay, so that's like the starting point, your initial amount, that's your time 0. Okay? All right, now let's look at the next thing they ask you to find, or explain rather. They ask you to explain what this means. Okay, well, just like I said for number 3 and number 6, if we look at this number is greater than 1. So we know that there's a growth, correct? So this would be the growth rate. It would represent how much the population is growing by. Okay, a growth rate. Now let's talk specifically how much it's growing by. So this whole number here, if it's greater than 1, then we know it's a growth as opposed to a decay. Now what it's growing by is determined by the numbers that come to the right of the decimal. So what we're actually going to do is we're going to take this decimal right here. We're going to go 1, 2 places, okay? And then you can see that we've got 2.2%. So it's a growth rate of 2.2% per year. Okay? So a growth rate of 2.2% per year in the city of Brownville. All right, so then now it says use this model. So when they say use this model, they basically are asking you to use the equation. So let's go y equals 720,500 times 1.002 to the x power. And they want you to use the model to predict the year during which the population will reach this amount. Okay, so that's an amount. Now, you've done this in Algebra 2. There are 2 variables here, guys. There's a y variable and there's an x variable, okay? And if you read the question in the second line here, it says x is the number of years since January 1980. So this represents years, which means then this has to represent population. And since what they gave you here is population, we're going to put that number right in here. And then remember, what we normally would do is we would try to get the variable that we're solving for, which would be the x, by itself. Now remember, it's an exponent. I don't see any e's here, so we won't be ln'ing. But if we have an exponent, we know that we're going to be logging. So let's try to get rid of some of this junk first. So the first thing I would do is I would divide both sides by that 720,500. Okay, now remember, you've got a calculator for this, so there's no need for you to do anything in your head. I'm going to leave that number as is for right now on the left-hand side, just like that. And then remember what we talked about in the previous video. If we have an exponent, remember we can drop that down in front, and now I'm going to log both bases. So I'm going to log this ugly base just like that, and I'm going to log that base as well. So let me rewrite that. All right, so then we would have this, right? And then all we have to do is take that mess on the left, and we are going to divide out that log of 1.002. Okay, and then you have a calculator. Please make sure you're using alpha y equals. And now you're just going to take this left-hand side right here, alpha y equals, and throw all this in. And we are going to predict the year, okay? So why don't you take a second, pause me, and see what you get. And when you throw all of that into your calculator, you're going to get x. Oops, hold on a second here. Let me get my pen going. Sorry. You're going to get x equals 35.1671. Now, let's read the question, because it says predict the year during which the population is going to reach this amount. Okay, so this is telling us how many years. So 35 and change years have gone by, but that doesn't tell us what year that is. So we have to take this 35 and change, and we need to add it to the 1980. Okay, so we're going to add, whoops, forgetting my pen again. So we're going to add 1980 to that, okay? And let's see what we get there. All right, so we're going to add 1980. You can just put that in your calculator. And I have 2015, okay? And then I have 0.167, blah, 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 blah. Now, we can't say that, but let's think about this logically. If the population that we're looking at, our time zero is January of 1980, what this is saying is we're in the year 2015, that would be January 2015, and then plus we're going a little bit more. So if we started in January of 2015 and we go a little bit more, we're still in the year 2015, right? So then your final answer would just be 2015. Okay, well, the start of this is going to be a little bit different than the last question. So we're on number 12, which you will find on page 10 of your packet. So go to page 10 of your packet, make sure you're taking notes. So this is a little bit different, the start, like I said, but eventually it'll be very similar. So just look here, this C, okay, is your original amount, or your amount at time zero, just like we did with number 7. So this is an original amount. This is an amount after a specific period of time. So like 5 years, this is what the amount would be after 5 years. I'm just giving you an example. K is just a constant of proportionality. And I'll show you how we work that in a second. And T is always going to be your time. Okay, so you'll learn these pretty quickly, and you won't really need to look at this or memorize it. You'll kind of know it. But initial amount, and this is an amount after a specific period of time. Okay, so let's look at this one. So we have a radioactive substance. It has a half-life. Now, I know you've taken science at this point, and half-life means when you start with, let's say, 100 grams of something, after a certain period of time, it will reduce to half, which would be 50, right? Okay, so let's read what we have here. So we have a half-life of 10 years, and how much of 20 grams will be present after 100 years? Okay, so we're going to start by writing the equation, y equals CE to the KT. And we know that, let's see, our initial amount is 20. So we put that there. We have the E. Now, they don't give us this constant of proportionality, so I'm just going to put a K there, okay? Now, we do have what we call a half-life, so then that means if I start with 20, I'm going to end with 10, and it says in 10 years. This is like a two-part question, because I'm really not answering the question yet, because what I actually need to do is I need to find this K. The question wants to know how much of this 20 grams is going to be present after 100 years. Notice I didn't put the 100 in here. You have to use this fact of half-life of 10 years first, solve for K, and then we'll go back and answer the question, okay? So a half-life of 10 years, if you start with 10, after 10 years, you'll have half the amount, okay? All right, so then we're just going to go ahead and we're going to solve for K. So we're going to divide out this 20, which obviously gives me a half, right, on the left-hand side there, or 0.5, if you will. And then we have e to the 10K. Okay, so similar to the last one, but we have an e. So I want to bring this exponent down in front, but because I have an e, I'm going to ln both bases. So I have ln of 0.5 equals 10K times the ln of e, and remember the ln of e is just a 1. So then we can divide out here by 10, and there's my K value. So my K is the ln of 0.5 divided by 10. Listen, I would really encourage you not to be tempted to turn this value of K here into a decimal, because then what kids do is they round it too quickly and then they end up getting the wrong final answer. So just leave it. You have a calculator, not a big deal. All right, so let's go back and answer the question. So it says how much, that's an amount, so that's what they're looking for. How much of a 20-gram substance will be present? We know what the K is now. It's the ln of 0.5 divided by 10 will be present after, here we go, 100 years. There's your time. Now, you may look at that and be like, oh my gosh, what am I supposed to do with that? Guess what? You have a calculator. You can plug all this in at one time and solve. So that's what it would look like, okay? And you'll find your E button on your LN button, okay? If you look at it above the LN button in blue, it says e to the x, so you have to hit second LN. All right, so then all I did, if you can look, this matches this perfectly, okay? Just use your alpha y equals here, and this is what we end up getting. So it says how much of the 20 grams will be present after 100 years. Now, this is how much is going to be present. There's not going to be a whole lot left. It doesn't say what to round it to. If it doesn't say what to round it to, my suggestion to you is just to go out 4 places past the decimal and round it. And this 5 here, I would look to the number next to that to see if that 5 stays a 5 or rounds up to a 6. And that would be grams.